One of the senior guys from NASA headquarters is helping us out. He's one of these wise old sage guys. When we pitched the idea to him, basically says, cute pony, neat trick, why should I care? And really what that means is, I mean, it's pretty cool, okay? Neat trick, air launch, wow, great, so what? And his point was, yeah, but what does it get me, okay? And so we've got to go back and figure out now, sharpen the pencil with these recent results on performance and figure out what the potential is for cost savings and do some quick study on that. That'll show up in a little schedule I'll talk about in just a moment, a couple of slides. And that'll translate into what we think in real world you can save on taking this approach and use that to go get the money. Because in this day and age, you've got to earn your way into the game. Nobody just writes you a check because they think it's cool. Well, maybe somebody does, but they don't do that with us. And so that's where we're headed on this. The technical approach for phase 1, and this is the sailplane, and we talked about a lot of this, is to basically modify the sailplanes. We're going to carry a subscale rocket on this that weighs approximately 100 pounds. It's built by Whitting Hill Aerospace out in Camarillo. It is a 8-foot-long version of something called Mini Sprite, which was a DARPA rocket that they put together. It is a hybrid, using neoprene and nitrous oxide that is throttleable and reusable. And we carry that to approximately 8,000 to 10,000 feet, where we will try to characterize the lift-to-drag performance with and without the rocket. We're looking at doing some demo launches. Initially, we're talking about dropping at 8,000 to 10,000 feet, probably do it a little bit lower because we're not trying to put stuff to orbit. We're trying to actually limit where this can go as a test. The glider would release from the tow line, glide back to a landing on the North Lake bed. The glider would be instrumented and flown remotely, and I'll go into some of the systems in the next few slides. The droid over there, which was the airplane that was used in the ground collision avoidance software presentation last year, where we are flying collision avoidance software in a cell phone. And there's a video I'll show after we're done with this, will be used as the tow plane, okay? And it would take off and land under the control of an RC pilot and fly to altitude through the Piccolo autopilot. So, and the initial rocket launchers would be inert, subsequent would be powered. This is the technical approach on phase 2. We pretty much talked about all of that. Again, the big thing is a 100-pound payload to orbit at a fraction of the cost of conventional methods. And then this is the phase 3, which we talked about also, the 1,500 to 1,800 pounds. This is a big airplane. Rutan's numbers showed it to be a 175-foot wingspan, 44,000 pounds is what he came up with, towed behind a DC-10. The schedule, in terms of the timeline, everybody goes, well, when are you going to fly this? Well, we're hoping to fly the glider here later in the spring to altitude. That's what this phase is here, subscale model concept investigation flights with a 100-pound payload. The economic study I was talking about is here. We're hoping to take the results of this and the Rutan, Ray Morgan, and Georgia Tech studies and go get a little bit of seedling money to do some economic studies, and then based on that, get approval to do the rest of this. This is the phase 3. These are 3 flight milestones of the 3 vehicles. Basically, we put together as about a 5.5-year program end to end. There is some discussion about skipping doing the phase 2 and taking more risk and doing the whole thing in 3 years. I don't think it'd be as much fun, but I think it's actually doable. I don't think the risk is actually all that high on the idea. And these are the objectives we talked about on phase 1 with the model glider, and we'll kind of transition to talking about the model airplane side of things. But basically, we need to identify and characterize the technological, operational, and safety risk areas of the concept, and then this is the key. Identify, investigate, test, and implement the methodologies to mitigate those risks. Risk management is the key here. A lot of people fly airplanes. A lot of people test airplanes. We at NASA Dryden, we do it safely. There's no such, one of our test pilots, Roger Smith, said there's no such thing as a cost-effective failure. And he's right. So you want to get it right the first time. That doesn't mean you study it to death. There's a balance there. We're also going to capture high-quality onboard video documentation of the concept. We've got 4 cameras on board that we'll be recording data from. And we can switch in real time on a telemetry downlink from any of those 4. We're going to characterize the aero performance of the vehicle. The lift-to-drag ratio is a function of airspeed and free gliding flight with and without the booster, and also the stability and control characteristics of the airplane. The airplane that we picked to do this with is a VENTUS-ZAX. If you wander around the corner to Soaring USA, the biggest glider they have on display is exactly that glider. That's where we bought it. That's not an endorsement of the glider of them, although I will tell you they're a pretty nice group of people. The quality of the glider that we brought in is fantastic. The only thing that we've done so far to this glider, and the only things we intend to modify, is the center section that we built. That's a custom design that Leslie here in the third row did all the design work on, structural and aerodynamic, and the landing gear system because of the extra weight. There's little nuances like how do you do the toe attach and everything else. No, by the way, this isn't the model. This is a full-scale Ventus in the picture, but the glider that we're using is 1/3 scale, 5.1 meter wingspan. Assembled into, and that's a picture of it in the model lab with the wings on, with the Droid 2 in the background, to give you an idea of what it looks like if you haven't been over to the booth. And this is what it will look like, and that's what's on the poster over there. With the center wing section, which is 2 meter on this size, it's 23 feet, 8-inch wingspan. There's a wingtip extension that we could get for it that bumps it out to 27 feet. The rocket that's shown is the Mini Sprite in the 8-foot length size, right at 100 pounds. You can see obviously there's quite a bit of real estate underneath. What you see up here is the center. It's hard to tell, but that's a centrifuge that is not on the wing as built yet. That's a mock-up wing over there, and that's essentially to provide a couple of launch point locations on for the rocket, which is mounted underneath. So that small little square is the center fuselage. It also provides a location to do a tow, single tow off. You want to tow off of the nose of the center fuse. We're also looking at towing from a location here and here in a Y bridle. And there's some advantages in doing that. One of the things that you got to look at, the tow dynamic can make or break you on the efficiency. If you have a high tow location, you're towing above the center of gravity of the mated pair of the vehicles. You're putting a nose down moment in it as you impart the tow force, which means you have to carry up trim. If you carry up trim in the elevators, you're imparting a down force in the tail. Now you have to carry some if you're flying around stable, but you're carrying additional down trim, which means your L over D, that's more drag. So you want to carry the minimum down trim for the stability case you'd like. What you'd ideally like to do is tow through the location of the vertical CG, so there's no moment imparted to the airplane. And the best way to do that would be to attach near the CG if it's practical. You can't do it if you attach to the front. On the other hand, if you attach to the front, there's some natural stability and tow effects. And we verified those on the F-106. Forger was literally able to put his hands up on the dash and just steer the airplane around with the rudder pedals. He didn't even touch the stick through a lot of the flight. He didn't have to, because you get a lot of natural stability under tow. It gets a little more complicated with the Y bridle, and those are the sorts of things that we need to investigate. Tow aircraft, we'll talk about the Droid a little bit. It's an airplane we've been flying for several years. It's a Bruce Tharp Engineering modified Super Flying King. Leslie can go into the details after the meeting on what the mods were. The really unique thing about the airplane, and we're using that here, is it's capable of being flown in 4 different modes and interchangeably switch between them on any given flight without a whole lot of trouble. You can take the airplane off and fly it around as a model airplane, and with the ground transmitter completely bypass the autopilot and the ground control station. And they literally, that system can't do anything, it can't take control back, you own the airplane. You can also take off in manual mode with an RC transmitter buddy box through the ground control station. The ground control station is a ground computer that drives the autopilot remotely with commands, fly by mouse, send at waypoints, that sort of a thing. At the presentation last year, there was a van, a bread van sitting here that had a ground cockpit in it. And that was being shown. We had a little sim running in that with the Droid on display. That's the ground cockpit that we're going to be using, where you can also fly the airplane from inside a van with a camera out the nose from a ground cockpit. Our test pilots are the ones that typically fly it that way. Or we can go autonomous. Autonomous is one of these loosely defined words. In our context, we're sending it waypoints, and it flies from A to B to C to D, et cetera, et cetera. Like I said, we can switch between all 4 of those modes during the same flight, and we routinely did that on virtually every one of our GCAS, ground collision avoidance software flights. The airplane weighs about 48 pounds empty. It can and has flown, I believe, up to 80 pounds. On the order of 100 knots is about as fast as you go with fuel in it. It's got a Desert Aircraft DA-100 LL in it. Flight duration is about an hour. We do not fly it with a flight termination system because we do have the capability of taking over control manually. We do have a range safety office at NASA Dryden, so we do meet all of the range safety requirements that you'll hear a lot of people talking about. I'm saying that not because the AMA president is standing in the back of the room either. I actually ran the range safety office at Dryden for 4 years, and I'm very sensitive to doing the right things and making sure we do it right. In fact, a little bit of bragging, the Predator flights that we have done to support the fire missions over the years, the FAA actually came to NASA Dryden to ask how we were doing it so they could use it as a model and litmus test for judging other people's proposals and how they were going about getting their COA authorizations. So we have a lot of experience doing this in a variety of sizes. Flight and ground systems, the airplane's equipped with the Piccolo autopilot from CloudCap Technology. It's installed it'll be installed in both aircraft, both the glider and the droid. Ground control station is basically a laptop computer through some avionics to send commands up and down at 900 megahertz, I believe. The support van, this is us with the droid sitting out front of it. This is where the ground cockpit and the ground control station are resident. The ground systems, this is the ground cockpit in a nutshell. It's a system where they basically reverse engineered a model airplane transmitter, but then set it up like it is a cockpit in an airplane. So you've got the throttle quadrant on the left, you've got the stick on the right for the pitch and roll axis, so you've got the rudder pedals, and the display that we use is much bigger than that. It's on the order of a 50-inch display with a full HUD. And then this is the RC transmitter that we use for the safety pilot side of things. Command and control link. Basically, this shows the link from the ground cockpit. The cockpit inputs go through USB into the ground control station, get limited up to the airplane and to the Piccolo. And again, at any point in time, the safety pilot transmitter can take over and cut that completely out of the loop and take full control of the airplane. And it literally bypasses the Piccolo and does commands directly to the servo. So it's, at that point, it's just a big model airplane. In the flight operation that we're going to be doing with this, we'll be flying the droid. Basically we'll take off with the RC transmitter and then pass control over to the ground control station here where they'll send commands up to the Piccolo. The glider will be flown from the ground control station always, unless we get into a problem with the ground cockpit with the HUD. So there's a video image that's coming down from the camera, but they're basically two separate systems with two separate ground control stations. And the way we're doing it is we'll take off with the droid flown RC style with the glider in tow, but the glider will be flown as if it had a pilot on board with the camera, with the pilot on the ground, stick and rudder with the cockpit. If there is a problem where we go lost link in either case, the Piccolo autopilot could take over and go to a waypoint and descend in altitude. Once we get to about 500 feet with the droid, we're going to hand off control to the Piccolo and have it do a climbing racetrack oval pattern to altitude up to about 10,000 feet.